Morning. My name is Mike Acton, and today I'm going to be talking a little bit about what we did with the LED and culling systems on the Megacity demo, which I hope everybody had a chance to see. I'm working on along with our team, on the new data-oriented tech stack that we're building. And a lot of what I'm going to talk about today is in relationship with that. So not just ECS, but the whole sort of mindset of how we approach problem solving. Here's some shots of the city. So lots of detail, as we've discussed. So a lot of stuff to, in fact, cull and manage with LED. So let's just get straight into culling. So per frustum, we need, and each frustum can be somewhere between 6 and 18 culling planes. We need to cull all the appropriate objects. In this particular sample that we're running with the Megacity, we have 5 views running. We have 1 for the main camera and 4 for our shadow cascades. So we need to cull the world 5 times. The world itself has a very extremely deep hierarchy. You may have seen Martin go through, break it down and show you how the building was put together with all the nested prefabs and all the things. There's a very, very deep hierarchy in each individual building or world section. Each individual section of the world has somewhere between 30 and 200,000 instances. So all that needs to be managed as part of the LED and culling passes. So in the whole scene, there's approximately 5 million instances that we need to cull or manage with LED. And it's relevant, the whole number is relevant because in the editor, you have the whole scene loaded. You may have a subset of that as you're streaming through the world at runtime, but in the editor, we want you to be able to, in our case, we wanted to be able to load the whole scene and actually work with it at interactive frame rates in the editor. So the performance of being able to cull and manage LED for the whole scene all loaded all at once was important. So let's start with the beginning. The first question that we need to ask as we approach really any problem space is, what's the least surprising thing? What's not surprising about the data that we have, so that we don't do anything that we shouldn't do, basically. The most not surprising thing about the world is it's static, for the most part. It's a city, it doesn't move, it doesn't transform into a robot or anything, it's a city and it sits there. So we can take advantage of the fact that our world, in this particular case, is essentially static. Putting aside the traffic and the cars for the moment, the vast majority of the world is actually static. So one thing that we can do in this particular case is take advantage of that by flattening the hierarchy. So as I said, the hierarchy is extremely deep, but what we don't need to do is do all of those transformations, right? Transform from the parent to the child every single frame. It's unnecessary because we know it doesn't move. So if we look at hierarchy, so some subset of the hierarchy like this, you have position, scale, rotation, and some children which also have position, scale, rotation. You can imagine how deep that could be, many, many thousands of objects and however many hundreds of levels deep that is in a particular building. And what we do is we basically just pre-transform that into a set of local to world matrices. So these are in fact the components the frozen components that go into the entity world. So along with the local to world transformation components, we have render bounds. So for each of our render instances, they have bounds. So basically an AABB that tells us how to call the object. And those are defined in local space, as you might imagine. This is the sort of the size of the object. But because we know, in fact, in advance, the local to world transformation matrix, we can also do a similar transform with our render bounds and build out components that are world render bounds. So basically pre-transform our render bounds into world space. Because again, it's not surprising that the world doesn't move in our case. So we have basically this set of components, local to world and world render bounds that define each of our instances. And these are really simple components, as you might imagine. So local world looks like this. It's just a float 4x4. World render bounds looks like this. It's just an ABB. So this is really legitimately what our component data looks like. So you can imagine at this point it's basically a flat list of 5 million instances in basically this format. So what's the next step? Calling a flat list of world render bounds over 5 million instances 5 times is probably not going to be the most performant approach that we could take. So we need something else. So the question is, do we do some kind of hierarchical spatial tree, some, quad tree, oct tree, something special here to organize this data? But before we got to that, before we decided to make a decision on this, we took a step back and said, what does our data actually look like? What are we dealing with? So in fact, our data is grouped. So all of our data inside the entity manager is grouped into 16K chunks of component data. That's by default, that's how it works. So each one of these sections, it's not just one giant flat list of 5 million instances, they're grouped into chunks of 16K. And in fact, because we have built out each one of these sub-scenes, like a building, they're roughly spatial. It's inside the same sub-scene, therefore inside the same building, and we can say something spatially about the groups of chunks that are close to each other. So the next step, what we did here was, for each chunk, because we know the chunks exist and we know they're roughly spatial, we added chunk world render bounds. Again, we can pre-calculate this, so we can say basically just combine all the render bounds for all of the world render bounds for all the instances in that particular chunk, and say here's the combined render bounds for that particular chunk. We do that for each one of the 16K chunks. A chunk world render bound, as you can imagine, is also a simple sort of component. It's just an ABB, similarly. It's just the combined one. So this leaves us with around 60,000 chunks, which is a lot better than 5 million. But that's still per each view. So we have to go through 60,000 chunks for each view as we want to cull in the world. Still a lot better than 5 million for each view as we want to cull in the world. So the next question is, do we want another level of hierarchy, right? Is 60,000 enough? It's a reasonable number, maybe that's fine, or do we want another level? So before we decide anything else, before we say we want an oct tree or something crazy on top of those chunks, let's take a step back again and look at the data again and see if there's something else here. So if we walk all the way to the end of the pipeline, how does this data actually going to be used, right? That's the question we generally need to ask ourselves. And what we ultimately want to do with the data is render it. So we have to say, how does our renderer actually work? What does that data look like? And it starts with a mesh renderer, which is a shared component. And a mesh render for our render batches basically requires a set of local to world transforms. Render this mesh at these locations, at these instances, basically. And you have multiple of those. So for every type of thing that you want to render, you say, here are all the places you want to render it. It's fairly straightforward. And if you have the same mesh that you want to display twice, so in fact, in multiple chunks, let's say, the render batch would combine those into one batch and then enumerate them. So we could have 2 chunks that get put into one single render batch, for instance, because they both share the same renderer. So that would be numbered 0 through 5 in this particular sample if you had 6. And then we would have a separate list of output indices for the actual render batch. So in case we say we decided to call those 3 individual objects, the output index list would look like this, where we just say, I want to draw, of the list of local to world matrices that I've already given you as a render batch, I only want you to draw 1, 4, and 5. So separately we have this index list that we send to the renderer. So the render batch index list is the format that we rendered to. This combines chunks that have the same mesh renderer and has a maximum number of 1023 instances, which is a pretty arbitrary limit, but it is the limit currently. So that's the world that we need to, that's what the data looks like that we need to push into. So can we use this data to make any decisions regarding our culling? So if we go back to what our chunk looks like, for culling, it looks like this, right? Remember, we have local world components, world render bound components, and a chunk world render bound component per chunk. So we also, of course, do have a mesh renderer component in there. So in addition, that exists. So we have multiple chunks. The mesh renderer is a shared component. If we take out the stuff that's specific to culling, we're left with this, which looks a lot like what we need for the render batch. In fact, it's exactly what we need for the render batch. So a render batch, in fact, is just a native array of chunks. That's what we need. Say, these are the chunks that belong in a render batch. And in fact, that by nature gives us a second level of hierarchy. A render batch is already a second level of hierarchy. So what about streaming in and out different subscenes? Part of what we were demonstrating yesterday with the Megacity demo was the ability to stream in and out subscenes of the level. So how does that help if you have already existing native array of chunks and some get loaded in, some get loaded out? How do you manage that? How do you keep it up to date? Well, the answer is we keep it really simple. We have a shared component, that is what subscene you're in, and then we don't allow render batches to be created across subscenes. So you have a render batch of chunks that exist in the same subscene. So let's go back for a second to this point, which we have, where I said you have an array of chunks. And if you have used ECS up to now, this is probably not something that you've done. You probably just haven't stored chunks in a native array for any particular reason. So the question is this safe? Is this something you can actually do? Or will the chunks change out from under you as ECS moves data around and moves chunks around, which is its purpose, right? Its purpose is if I change some component, then chunks get moved around and it gets pushed in a different, changed. If I delete some component, the archetype changed, then that component data gets moved into another chunk. That's how it's supposed to work. So all this data is supposed to move around. So is it safe to hold on to these chunks? That's where we enter this particular function. And this is a particular function that I think is important to understand the safety of keeping data or caching any data related to chunks or the layout, the structural layout of the entity manager and entity component system. So gate component order version. This tells you specifically if the structural order of a particular component type has changed. So for component type position, you have conceptually the list of all the positions in the entity manager, right? A conceptual array of every position that exists in your world. If anything, any one of those has moved for any reason, so one is deleted or one has moved because the archetype changed or anything like that, so the structural organization of that conceptual array has changed, the order version gets bumped for that particular component type. So imagine we have a component type A and a conceptual array of A's, a component type B, and a component type C, right? 3 components. The thing that we care about in our system is we require component type A, B, and C. Let's say these are 3 required components in our system. I want to cache information related to A, B, and C. For instance, a native array of chunks. So how do I do that? So there's 2 cases that we need to worry about. One is that something outside the set that I care about, A, B, and C, has changed. So for instance, somebody's deleted component A, that particular component A, which is outside of the set of components A, B, and C, that sort of combination. What happens? Well, it gets deleted, and the chunks get moved and basically shifted over. And so version A here changes, right? The structure of A changes, but the structure of B and C didn't change. Because there was no A that affected the chunks that B and C were in. So there's nothing to worry about there. But what about if I change something inside the order set? So in this case, let's say I want to delete A here, where it's inside of a chunk that has an archetype that includes A, B, and C. So this causes B and C to change their archetype. So I delete A, and B and C get moved to a different chunk in a different archetype. And in this particular case, all the order versions A, B, and C are changed. So that means what I'm looking for, and if I'm caching any data related to all the required types in my particular archetype, the thing that I particularly care about, is if all of the required component order versions have changed, my chunks are invalid. If that's not true, then I can continue to keep the valid data that I've cached. So the question of, is it safe? The answer to the question of, is it safe, is yes, so long as you're careful about knowing when things could have changed. So the culling loop itself is super, super simple, right, at the end of the day. We have a render batch, and inside the render batch, it has a set of chunks. Those chunks are inside of a single subscene. For each of those chunks, we have the chunk render bounds, so we check to see, is this bounds inside my frustum? And assuming that passes, then we can check the render bounds for each individual instance inside that particular chunk. Obviously, we skip the chunk if it doesn't pass. We skip the chunk entirely if it doesn't pass. And then if that particular instance passes, we add that instance index into the batch index list. And then we do batches in parallel. So that is, in fact, the whole of the culling loop. That's it. The main thing that we, I think, accomplished here is not adding a bunch of stuff that was unnecessary to solve the problem, right? What we did was say, look at the data that we have. There were two key points, right? We looked at, this is the chunk data that we have already laid out. So therefore, we already have a first-level hierarchy organization of our data. So all we need is render bounds for that. And then we looked at, say, what does our output data look like, which is batches, and which has already grouped our chunks together. So we already have a place to do a hierarchical output for that. So we didn't need to add a bunch of complexity to our system. There's a lot less moving parts because we understood what the data layout actually was, right? And that is a critical part of the whole concept of data-oriented design, and ECS in particular, is that data transparency, right? That you can understand, you must be able to understand what the data looks like in order to make good decisions about your data. Your first instinct to add a bunch of moving parts, like octrees or whatever your solution might have been, would have been unnecessary, was in fact unnecessary in this case, because that structure already existed, or something like that structure already existed that you could take advantage of. So our culling loop looks like this. It's in fact one simple job, which is one simple function that just does this and manages our whole scene. So let's talk about LOD. So in the same way as we flattened the culling hierarchy, we also flattened the LOD hierarchy. So one simple observation with LOD is that if you do the same LOD calculation twice, you get the same result. So we have, you can imagine LOD as a hierarchy. So you have some LOD node that points to, say, the low model and the high model, right? And the LOD node may say what is the minimum distance and the maximum distance, and what's the reference point, and then I can select either the low model or the high model depending on the results of that calculation, right? And then you have a hierarchy of that. So you can imagine that that's how it works, and that's basically how it works in the editor. But if I instead said, I'm in fact going to flatten that. So what I have is LOD0 over here, which does the exact same test as LOD1, right? But the minimum and maximum distances are different. In fact, they overlap. They don't overlap, right? They're right on a line with each other. I do this test here, I do this test here, And when LOD 0 is correct, it'll just draw this one. When LOD 1 is correct, it'll draw this one, right? I don't have to have the hierarchy. I can completely flatten the hierarchy. So I just separate out each LOD into its own component. But there's still groupings of LOD that we need to manage. So if we imagine, again, our local to world component matrices here, we can have an LOD 0 that is a bunch of them, right? At LOD 0, draw all of these things together. But that's not always the case, right? Sometimes we have an LOD 0 that's just the one renderer. Sometimes we have an LOD 1 that's just the one renderer, whatever. So it's a case where this is an arbitrary setup by the artist, right? It may be a group of mesh renders, it may be a single one, it's an arbitrary grouping. Similarly, we have the hierarchical LOD, which can do the similar kind of thing. It can take a group of LODs. So in this case, HLOD 0 might be those two LOD zeros, and HLOD 1 could be those two. So the next thing we did, right, again, as a pattern, is take a step back and actually look at the data. We looked at our scene, we analyzed the scene, we tried to figure out what is the appropriate approach for our problem. And one of the things that we discovered is that most instance LODs are actually unique. So they're not combinations like, I want LOD 0 to be these three objects. Most of them were referring to a single object. Most, not all. And so what we decided to do is say, let's just flatten that out. Instead of dealing with the complexity of having this sort of grouping and hierarchy, we're just going to flatten it out so that we have one per individual object. So this maps perfectly well to having a component in that case. And in fact, that component data looks like this. Have a world reference point. Again, we can pre-calculate the world position reference point because we know these things are static. And a min distance and a maximum distance to render this particular LOD out when you're between those two. And relative to the hierarchy, that min distance, max distance can be pre-calculated as well. So all of that can be pre-calculated. And that's literally what our component looks like for that LOD level. So what about HLOD? So if we look back at our chunks, remember we have local to world and world render bounds and chunk render bounds, mesh render, and subscene shared components. Those orange ones are shared components. So remember that before culling, we have chunks. These chunks must, if they're in different subscenes, they must be in different chunks, right? We've separated them out by subscenes by that subscene shared component value. Based on this fact, and looking at the data itself specifically, two things. One, because they're in the same subscene, so they tend to be they are in the same building or the same area, and they share the same mesh renderer. So, it's this detailed object here, and however many instances of that detailed object is, or this face of the building, and how many different places of that face of the building is. It shares the same mesh renderer. Because of that, 99% of the chunks have the same HLOD root. Because it turns out that if you're drawing a detailed object, it tends to always be in the same LOD level. It tends to be an LOD 0. And if you have a big object, you tend to use it at the same LOD level. You tend to use it at LOD 1 or whatever. You very rarely will say, take this detailed object and put it in a higher LOD level. So the same objects always tend to be used in the same LOD level. That's by design. That's why they were designed to exist in the first place. So it makes sense. It's not 100% of the chunks have the same HLOD root. We did discover a few cases where artists had selectively picked things to be in a different than designed root, but very, very close. So we could have split the chunks where there was an exception to that and made sure that this was true 100% of the time, but we didn't. So what we have is, what we ended up with is for each individual chunk. So we have a chunk, in this case, will have the local to world components and the LOD components associated with each instance. We have an HLOD component, which is what the root of that chunk is, and a count. So the number of instances from the top of the chunk that HLOD applies to. And then in the very rare cases where we have another one, it can have a second component that says the next HLOD and its count. In this case is just 1 at the end. So what we're doing here with the HLOD is just checking the root of the hierarchy, right? So like say the building. So the building root is not visible from an LOD point of view, right? We're outside the LOD range of the building. So the details of that building cannot possibly be visible. We skipped all the LOD inside that building. There's no point in even looking at it. So all we do is check the roots across the board. So that gives us 99% of the hierarchy, the actual hierarchy tests that we need to manage. The in-between is all basically pre-baked into the final test of the LOD in orange there. So the LOD loop itself is also super simple. For each chunk, we check the HLOD root. For each of the HLOD roots that we have in there, most of the time, the vast majority of the time, this is only 1, but sometimes it's 2. And assuming that passes, assuming it could possibly be in this HLOD level, then we check the LOD levels for each individual instances, because those instances can pop in at different rates than the whole of the object. And then for each one of those that passes, we pack the result into a bit set. So did this pass, did this pass, did this pass, right? That's it. So we pack the results into a bit set at the end of the LOD loop. That's it. That's the whole entire LOD loop in the sample. And chunks are done in parallel. So how do they get put together? So first, what we do is we do this we do the LOD loop for all the chunks. And then we call for each view. So calling view 0 based on the results of that bit set. So calling on view 0, view 1, view 2, view 3, view 4. That's what our update looks like in terms of LOD and culling. So let's look at the culling loop again. Remember, for each render batch, we went through each chunk. For each chunk, we checked each render bounds. And assuming those passes, we checked the world render bounds for each instance. And assuming those passed, we put the index of that into the batch. But we can, in fact, early out based on the LOD visibility, right? So this is one thing that we added to the chunk loop, to the culling loop. So for each chunk, here, before we check the chunk render bounds, we check that bit set to see if any LOD in this chunk is visible at all. If there isn't one, we just skip the whole thing. So that skips a great deal of the per view culling that's necessary. No LOD could possibly be visible in here, so why am I even checking the render bounds? So that's the entire LOD and culling loop for the sample. So to recap, the culling loop is super simple. The LOD loop is super simple. But it's simple because we could reason about how the data was stored, because we could reason about the components that we're dealing with, because we could reason about what the render batch looked like. And we could get some basic statistics on the problem that we're specifically solving. So the key to data-oriented practice is data transparency. Understanding what's there is how you solve a problem. Hopefully this overview gives you a chance to understand what we're doing when you have a chance to see it. We'll be releasing all of this, everything that we did to make the demo next year. So hopefully this is enough to understand, there's obviously devil in the details, right? To understand why things are there and how they work from a very high level. So that's it. Any questions?
Amazing work. Awesome. Occlusion culling.
That's a story for a different day.
I knew it.
Yeah.
Anyway, when you guys talk about streaming in your LODs, all those assets exist on disk locally,
Yeah.
right? Nothing streaming from network or any of that.
Yeah, in this particular case, it's all streaming off disk.
All right.
Yeah.
Cool. Thank you very much.
That doesn't exclude the possibility of doing something else, but that's what we're talking about here.
Hi. You mentioned that the entities in the same chunk are spatially close. Is it just because of like instantiation orders or something you're doing to pack spatially close things into one chunk?
They're spatially close-ish, right? Because of two key things. The observation that they are in fact built together in a subscene. So like this building is one entity world that creates one subscene. So they must be roughly spatially close because they were put in the same building. So that's one observation. They have the same subscene tag. The other one is that they share the same LOD level and they share the actual same type of mesh instance, so they tend to be grouped together physically. So there's nothing specifically that we're doing to spatially group them. It just turns out that way based on the nature of the data that we're dealing with. So we could do more to say, do something special to sort them or do something, make them more spatially close, but they were close-ish and close enough for our case.
Hi, can you briefly discuss the pros and cons of storing the chunks in a native array versus just stuffing that like in another component data and making a system out of that?
No, you could do that too. And this is something that we've gone back and forth with, and we may land onto creating a separate set of entities with component data that's specifically pointing to chunks. So yeah, we could do that too. And I don't know that there is a good list of pros and cons other than it was convenient for me at the time. So yeah, we'll look at that and try to decide which is the better route.
Great, thank you.
So when you're authoring each of these subscenes, you obviously author them with the full detail.
Yeah.
Do you then have tools that generate the levels of detail from those meshes to instances further and further away?
Yes.
Okay.
Yeah, that's just specialized tools that build the HLOD stuff for our artists.
Okay, thank you.
Yeah. Okay, I think that's it. Thank you all for coming.